Okay, let's talk before lunch. So how things change with scale. So this is the title of the talk, or also how the bias parameters run, or also if you want, how we dubbed it the randomization group for LSS. So this work was done in collaboration of these people, many here in this room. And so the main, message to take home is that we took something that's very widely used in high energy physics, which is this semantic equation that describes how a coupling parameter changes as a function of scale lambda. And this is given in the right-hand side here by a beta function of the theory. And we basically generalize this semantic equation to something that we can use for galaxies. So this is the bias parameter. The analog of the coupling constant here would be the bias parameter that we have, or the counter terms, for instance. And this expression, this very simple expression, tells you that a bias parameter A changes with lambda by just a linear combination of the other bias parameters B here with some number S. So this S here is a simple matrix. And what drives basically how fast those parameters change is basically the variance of the linear density field on the same scale lambda here. So I'm just flashing some results that we had in this recent work. And you can see this B1, basically the linear bias changing as a function of lambda. And each one of these sigma square orders here is some higher order contributions. And what the RG gains for you is basically to interpolate in between all higher loop contributions that adds a sigma square contribution, and magically, interpolate resumming kind of high order contributions. So here on the right, you see the one loop result. So this sigma square is usually what we subtract when we just consider the normal sigma square contribution. So when you solve the full one loop RG, you gain something like this blue line here. And the two loop RG, as we're going to see here, is pretty small. So just add something here. And there's actually something meaningful in the fact that the two loop RG is small. And this is what I'm going to try to explain in this talk. Right, so before that, let me just flash some results of other work that I had this year together with Thomas, Elisa, and Zvonimir. So we basically had this fast two-loop evaluation in which we were able to extend like the one-loop calculation, doing like the two-loop calculation, and we see something around 20 to 30% gains in cosmological parameter, and going from K.11 to 0.26. So if you want more about that, please look at Thomas' talks last week, I think it was. And back to the RG, the intro is the following. So it's pretty interesting to understand, from food to galaxies, how things change with scale. So this is a broccoli here. So I was just giving this talk at some point, and someone raised their hand and said, do you know that Rubin first image was also a broccoli? So I said, okay, I'm very excited now, So people are really motivated by broccoli and digging into how things change with scale, and also galaxies. If you zoom in or zoom out galaxies, they also have this pattern that we want to understand. What happens with galaxies as we zoom in or out. And you see that it's quite different than broccolis, because here we don't have these self-similarity scales, but we see some things like you zoom in and still have some network here and some things to understand, right? So this is what we're trying to understand. And it's actually cool because when you ask yourself how things change with scale, or something else, an alternative title for this is how to use a one-loop renormalization group result to gain information about higher loops. Is it possible to use a one-loop RG and actually gain information about higher loops kind of for free? And this comes from something that's called methods of regions, like in high energy physics. And the intuition is the following. The one loop to some power n, there's a region in this phase space integral that actually resembles quite a lot an n loop integral. And you can split this two loop here, for instance, like P and Q here, as a region P larger than Q or Q larger than P. And this part in which you have this hierarchy between the momentas is actually absorbed by a one loop square contribution. While the P close to Q, like the other region in this method of regions, is what we call intrinsic two-loop contribution. And to get this piece, you would actually have to compute this two-loop contribution. But there is a part actually that's absorbed by this one loop to the n power. And this is what the RG kind of gains, gives you for free. Right, so QFT 101, and what the RG is that you have these couplings, and they change as you change scale. But you think, okay, those couplings change, but what is intrinsically physical are the observables, right? So the observables should not change. But what coordinates how the couplings change is what's called semantic equation that I just described. Then you can ask what happens in the context of galaxies. And in the context of galaxies, we have an OP, operator product expansion, in which you write the general galaxy density field as some expansion of bias operators and stochastic coefficients, and here are those coefficients. And they receive contributions, the composite of operators like with square and third, receive contributions from very small scales. So we actually have to renormalize those guys. So when we renormalize those guys, we had some lambda dependence here that tells you how each one of those should evolve as you change zoom in or out. And one alternative to deal with this lambda dependence is one, to renormalize it. So define some renormalized operator in which it's a lambda dependent part plus some matrix Z that counterbalances basically the lambda dependence of this guy. And then you can do some RG conditions, basically say like, okay, this should expect some endpoint function matching, and then you find basically this matrix Z. Looks complicated, but we did it at fifth order. We have a long table of coefficients. You can calculate these Z's, for this huge number of operators. Nice. But the alternative number two is to live well and just assume those bias actually depend on lambda. And if you go back, to our masters like Polchinski and ask, okay, what do they think about it? He says originally, renormalization was just a way to remove infinities from perturbative calculations. But a great improvement comes when we take seriously this lambda dependence of the operators. And then we can learn something with that, right? So the idea is that there is this renormalization picture in which you subtract the lambda dependent part, and there is new framework that we have that depends on lambda. And actually, they connect to each other when you take lambda and bring to zero. So you just run your bias parameters towards lambda to zero, and this gives you this separate universe picture in which the bias are renormalized. Then let me move to the equations, how we derive the equations. It looks a bit complicated, but we just say that, okay, delta G should not depend on lambda. So it means that how the bias operator change with lambda is actually dual on how the operators themselves evolve with lambda. And then you can expand this dBA d lambda as a one loop contribution and a two loop contribution. Then you calculate this. You just go to this, plug in back and calculate basically these coefficients here, these S coefficients that tell you how a bias A depend on the other bias combination B. So it's just a rotation in these bias bases, right? And then you can put it in a table. So this is what we did first. And then in this work that came out recently, we basically generalized it to two loops and also fifth order propagators. And now you have some D coefficients here when you do the two loop computation. Looks complicated, but again, you go put everything in a table, calculate this, and just solve those ODs. So one pretty nice properties of those solutions is that they depend on something called the single hard limit. So the one loop result depends on something called the single hard limit of the K kernels. And this connects basically the n plus 2 kernels with n kernels. And the two loop result connect the n plus 4 to the n kernels. So it's just some kind of very systematic way to calculate those things. And the two loop result depends on this D function here. And this D function is something that depends on the ratio of the momentas P and Q. And there is when you split this in two contributions, there is an intrinsic one loop square contribution that we call, and another part which is an intrinsic two loop contribution. So you can find that these intrinsic two loop contributions is actually when both momenta P and Q are close to each other. Exactly this method of region that I was describing before, right? So we have some hierarchy of P and Q. This gives you this guy. When you don't have, basically this is what sets the running of the intrinsic two loop part. Right, let me move to the solutions. So the one loop solution is actually rather simple. It's just an ODE. So this tells you how the linear bias evolves as a function of lambda. And this is a combination of the other parameters. The delta square part you also have here. So you see basically you plug in values, initial conditions for those guys, and you have how the running of those guys evolve as a function of lambda. And this for some fixed initial conditions is what I'm showing you here. And then you can draw these very nice diagrams that explain you how the linear bias evolves as a function of the quadratic bias. Right, why you should care, why it's relevant. So the first thing you can do is to diagonalize this basis. So you can rotate and find basically diagonalize a base that's diagonal. Then you can write this solution in terms of some eigenfunctions. So eigenfunctions with eigen coefficients lambda here. And when you diagonalize this basis, you find that if you restrict yourself to the second order bias parameters, you find two zeros for the eigenvalues and one negative guy. In the QFT language, this would say like those guys are marginal here, whereas this guy here is relevant. So this tells you that if you start here in the IR and evolve, basically you have zero modes like marginal modes that are constant as you evolve, and one guy that decays. Basically this guy, so the evolution here basically gives you something that's constant because everything then should basically decay by this guy here. Right. The next thing is what happens when you extend to third order calculation. And this is something we did in this work. And you not only find the marginal operators that you had before, the zeros, you find also some extra relevant guys, but you find one mode, one of the third bias coefficient, that's what we call irrelevant. So this gives you a positive coefficient here. So what I want to say and what I can say here are two different things. So what I want to say is that the fact that there is one irrelevant coefficient here basically tells you that when you grow to the UV, this guy becomes irrelevant, as the name says, right? So this guy is super sensitive to the UV. So we are still not sure about this because this, as you see, like as when you go to third order to fifth order here, basically you see some instability. You add new terms and you find a relevant term. So what happens when you go to higher order? But there is still a problem here, and we want to understand more what happens when you go to higher orders. Why you should care? Two. So the reason number two why you should care about these RG solutions. So the one loop RG, basically you can just solve this ODE and recursively plug solutions, like you just recursively solve this equation. And you find that the solution for a bias A can be written as a sigma square part that's proportional to sigma square, and one part that's proportional to sigma to the fourth, and one part that's proportional to sigma to the sixth. So this is what the one loop contribution is. This is what the one loop square contribution is, and this is a one loop to the third contribution. And then, as we know, like this simple ODE also admits an exponential solution. And what the RG does for you is to actually resum all those parts here. So if you just solve the RG, what you're doing is actually resumming all these higher power in sigma contributions in one single exponential. And this is what we see in this plot that I showed in the beginning, that basically all powers in sigma are resummed by the RG, right? So this is something that we find that's quite interesting. So the partial conclusion here is, okay, we find that the one loop RG resums part of the higher loop contributions in this special regime in which you have this hierarchy of momenta. But the other part, which we call intrinsic to loop, the question is it small? Because if this part is small, amazing, because the one loop is giving you most of the information. If this part is not small, then you would have to calculate the higher loops anyway, right? The RG wouldn't add much. So this means, okay, we have to do the true loop. So this is what we did. So the two loop solutions, when you calculate, as I showed you before, are actually small compared to the one loop. So this is very reassuring, right? We find something that's, if the fact that two loops is small means that the one loop squared, the one loop cubic is also relevant. The question is, okay, it's small, but is it parametrically small? And we find that, yeah, it is parametrically small. So we took some power law universe, so universe that goes in a power law. And what I'm flashing here is the result of the two loop contribution, the intrinsic two loop over the one loop square. And then we find that for a power law universe, when you go to -3 in the power law, there's actually this guy goes to 0. So this means the intrinsic two loops is small compared to the one loop. Also for lambda CDM, the ratio of the one loop square, the two loop over the one loop square is actually small. It's more than 1, 2. So this is very reassuring, right? It means that intrinsic two loops is small. So when we go back to the Kalit-Semantic equation that I was showing before in QFT, something very nice happens when we consider the fine structure constant alpha here, the usual textbook exercise for QED, and the usual solution of the RG for the fine structure constant. I mean, it's just some power law, the beta function here. And then you have the leading log solution here, which is something that goes with alpha 1 minus beta times alpha here. And when you expand this solution, you find something that's called the large logs, right? You have beta one loop and beta one loop square, but each one of those terms comes with a log term. And what basically the RG does for you is that if you have a scattering that you organize as some higher loops, so you have a scattering at 3 level, a scattering at 1 loop, a scattering at 2 loop, what the RG does for you is to resum this tower of these higher loop contributions. So it's a one loop solution that gives you basically an important piece of higher loop contributions. So this is what the RG does for you. And then the 2 loop RG resums the next 2 leading log contributions. So that's where the information from the logs come from, right? So you can ask yourself, what happens for galaxies? Do we also have those logs? And the analog of the logs that we found in the case here is that instead of having this mu over mu star, we find something like a power law, a 1 over n plus 3 expansion, n being the power law index of the universe. So we can reorganize the power spectrum at linear level, 1 loop, 2 loop, as a sigma to some power here, because each power of higher loops comes with a sigma square, times something that's like 1 over n plus 3 to some power. So this makes the whole of the large logs in the context of galaxies, right? So same way as you had here, we have here. And when you ask yourself, okay, let's go beyond the power law universe, we find that we just took some scale, like the usual log scaling of the power spectrum at small scales, And we find that it goes as something like log of lambda over K equality. Right, so again, what I can say and what I want to say. Oh yeah, I'm already over time. Okay, I have 10 slides, so I'm gonna be quick. Okay. Okay, what I want to say, what I can say. In high energy, the RG is very powerful. I mean, it's an important tool, and it basically sums these hydro loop contributions. But what I can say is, okay, we find these very interesting things, but we still have to understand better in between which scales the RG can operate. Because for the RG to work, like it has to integrate in between two different scales, and we still have to understand better what's happening here in this context. But we find interesting that it resums part of the information, and how big this information is something to be determined. Finally, flashing two slides. So PNG, so we have how delta evolves like when you add PNG, and it's very nice because when you add primordial non-Gaussianities, you have the usual term that you had before, the Gaussian free term, but you also have the new interaction term. So this work was done in collaboration with Karl Lampos-Nicolas, which was a master student at that time. And then you basically find also an ODE for the non-Gaussian bias parameters. And again, you put everything in a table, calculate those coefficients, and something nice that pops out of this is that you have the usual 1 over K square that appears when you consider PNGs, right? So this is kind of a derivation of the famous Dalal plus 2007 result. Finally, you can draw this kind of nice diagrams for PNG2 and stochasticity. Stochasticity is something else we dealt with. So you have the stochastic parameters epsilon here, and when you consider basically these epsilon coefficients cross-correlated, you have some C coefficients that we determine. What is interesting here is that we generalize also the RG to include stochasticity in a very simple form. So this C is the stochastic coefficients, and it's a very organized way to understand this stochastic series in terms of some extra Feynman diagrams. So stochasticity was also derived. Let me flash the conclusions. So it's a very nice tool also for cross-check of EFT inference. You can just plug this lambda dependence and check if you actually match the expectation. It's a very systematic way to renormalize, also including stochasticity, PNG. There is more information. This is something to be determined, and we're trying to understand this better. And still to be understood exactly like in between which scales the RG can operate and this RG stability of these relevant, irrelevant terms that I described when you go to higher order. And I leave you with the broccoli. So.
As you said, the RG is very useful when you have a large hierarchy scale that makes a log large.
Yeah.
Here, I don't see large logs. In the sense that even stretching is log 10, but like
yeah.
The problem of BCFT is something is that the cutoff is actually close.
Yeah, I totally agree.
I don't see like a big advantage in some logs scale. Actually, it be dangerous because when you're a sum and you don't have enough hierarchy, you might see, spurious effect by the fact that you're sum diagrams, via loops.
No, I could not agree more. I could not agree more. This is something we are understanding. We're trying.
Irrelevant operators, but this is actually what I would expect in an EFT. But at some point, I need to match to some UV theory. So this will give me the. Actually, I think the surprising thing is that you get a lot of relevant direction, which is because the power spectrum is very converged.
Right. So, okay, for the first question. Right. So the first question about the logs. I could not agree more. We're still trying to understand better in between which scales we can resum those logs. If there is any bispectral configuration, regime like basically squeeze regime or something that we can resum. This is something to be understood better. But I don't have an answer for this yet, and this is something we are trying to understand better. You're right, I could not agree more. The second part about the relevant, irrelevant pieces. So my expectation was nothing, to be honest. I was surprised because we always said, okay, like you have to consider all those bias. They all should be included. And I mean, I didn't have any naive expectation. I just found interesting that we found one irrelevant one, and that this guy runs like towards the UV and grows towards the UV is something. I mean, should we keep this term? How sensitive to small scale physics this guy is? It's something that it's interesting. We should investigate, because this guy, if this guy is super sensitive to UV physics, maybe there's a reason to drop this guy or not. This is
at some point, say at some scale that match to a certain completion, we could even do the simulation of the laser equation.
Right, right. So you find like, okay, if this guy grows,
Of course, if you follow RG, the RG of the EFT, you will see this operator exploding. But this is effective computing the RG within the EFT.
right? So it kind of tells you that there is a breakdown to know that if you add new, I agree. Yeah, but it's nice because the fact that you add new operators and it adds kind of an irrelevant operator tells you that, okay, this is where these terms, the terms that were before, now are irrelevant, right? Like kind of you have to add new guys to complete this. And this have been, I mean, it's intrinsic, as you said, it's intrinsic from EFTs.
The sign of the sign. So they're all marginal.
They're all dimensionless. Yeah. So it's not about particle reducible and particle irreducible. It's not the usual split between particle reducible and particle irreducible diagrams. So there is a part of the true loop when you expand, if those logs are big, if you can, there's a region of the true loop diagram that can be understood as a one loop square part. If, well, this is not no, this is not exactly the same that's canceled by the counter term. This is an intrinsic loop part. That's the second order part. No, this is like the leading part. The leading part is here. Like this is the piece that's there in the loops. So this is not like the usual k square over p square part. The counter term will take care of the k square, like higher derivative part. This is not the higher derivative part. This is like an intrinsic loop part, like. So, so the extra information is that there is a piece of the intrinsic true loop. So of the one, take the full true loop. You can break it in two regions. These two regions I explained, and part of this region is nowhere already. It's fixed by the one loop part. So this is what I mean. Mare case. Ah, so for the matter part, you basically have. I mean, you just have the counter terms. In case of matter, you have part of this bias being basically zero, right? So this would be a subset, like a subspace of this RG already included. Yeah. So. Yeah, piece of like the counter terms, everything operates the same for the counter terms too. So you can also, I mean, I'm just showing for the bias, but you also have the counter terms running and all the, so these would also work same way for counter terms. Like this. Right? Right. So as I said, so when you take lambda and bring to zero, this should match the separate universe picture, right? So in principle, this value here is given you by this peak background split values or something. So you have two options. If you have a simulation like field level inference and you have some fixed lambda, you can start here and basically match the separate universe running towards lambda zero. Or the other way around, if you have like your values here at one lambda, like lambda zero, given by separate universe, you can run towards larger lambda and find something that would match some, field level inference. So this is the idea. Well, the intuition is that you collapse. When you have one of these two conditions here, you can understand this as kind of collapse in one of the loops here, right? I mean, no, this means physically, if you take the kernels, like the kernels, and take the limit, like the single hard and double hard limit of the kernels. So take this, the two loop part of the two loop, this, you're taking the double hard limit of a kernel. Part of this regime can be understood as a composition of two single hard. So you can write a double hard as a two single hard limits, as a product of two single hard limits. So this is the intuition. No, it is. It is. You have the phase space of P and Q here, and you have P, you have Q, and part of the region, you can imagine you're splitting P of Q into a diagonal part, which is Q close to P, and all the other parts, right? You have a square. So this is the intrinsic two loop, and this is the one loop square, right?